Hello everyone, it's a pleasure meeting you all in my mathematics class. Today let me discuss about the Tower of Hanoi. I have already discussed about a Fibonacci sequence and how the recurrence relation has to be formed and solving the recurrence relation equation, that is a difference equation of a Fibonacci sequence. Today, in the same lines, let me explain what is Tower of Hanoi, what is the puzzle, how the recurrence relation is obtained, and how to solve the recurrence relation that we get by in analyzing the Tower of Hanoi problem. Say this puzzle, Tower of Hanoi, is goes like this. Say we have got a peg like this. There is a peg like this, and we have got discs like this. Discs which are arranged. Discs which are arranged in the bottom or ascends from the top. That is, you see that this is a smaller one, the next small bigger, the next bigger. So it ascends. It ascends when it comes down and it descends when it goes down. So this is the tower in which you have got the discs bigger in radius, then slightly smaller, it goes on like that. Any number of discs, n discs can be there, n discs can be there, and these discs which are arranged in that descending order from the bottom, to another peg like this, another stick or a peg like this. There is another peg like this. You have to transfer all this in the same order, with the help of another standby peg is here. There is one more standby peg is there. You can make use of this standby peg and transfer it to the another peg in the same order as here, that is in the descending order from the bottom, and with conditions that number one, move one disc at a time. Number two, never stack the smaller discs on the, never stack the bigger disc. See, bigger discs on the smaller ones. So these are the two conditions under which these n discs have to be transferred to another peg. This is a stem like you have to transfer it here, and a standby. That is, you have got a helper stem is here. With the help of this, you can transfer here. With the help of this, you can transfer it to that. And see, and we have to transfer these discs in the same order to this disc 2. That means here this, let us suppose that this is a standby disc, this is a standby disc, this is a disc 1, this is disc 2. Transfer it to 2 with the help of this standby disc, with the condition that move one disc at a time, and condition number 2 is never stack the bigger one over the smaller ones. These are the conditions. Now let us see this. See here, if I say that this is the nth disc, then you have got here n minus 1 discs. And you see that this n minus 1 discs have to be transferred here and then to second disc. That is, we are going to make use of this standby disk, peg, and then transfer it to 2. That is, you are going to transfer it to 2 through S, and this n minus 1 disk will be transferred here, and also it will be transferred to the disk 2. So the peg 2, it will be transferred to the peg 2. So you see that here Sn, see I will call it as, this is Hn. This Hn means n number of, this is the Tower of Hanoi, so I am calling it as Hn. So n number of disks are there, and n minus 1 disks will be transferred here, and these will be, and ultimately you see that this one disk at the bottom, it will be given a just one movement to go to this peg 2. That is, the biggest of all the disks will be given one movement to be transferred to 2. So you see that one movement will be there, but all other is Hn minus 1 disks, n minus 1 disk will be given Hn minus 1 moments here, and then Hn minus moments there. So you see that we will have Hn minus 1 here, and also here H minus n minus 1. So you see that you have 2 times of Hn minus 1, 2 times of Hn minus 1, plus this one disk will be transferred, it will have only one movement. That is, with one movement it will be transferred from this to the ultimate peg 2. So you see that it involves only one movement. So the total number of moves from the peg 2 to peg 1 to peg 2 through the use of this standby peg is Hn. Hn refers to the number of moves to move the disks in the same order to the disk 2. That is Hn. This H is merely put in order to make you understand that this is a problem of Hanoi, puzzle of Hanoi. So this Hn will be equal to here Hn minus 1 moment and then another Hn minus 1. So you see the 2 times of Hn minus 1 and one movement from the last disk from here to that. So that is why this comes. So this is the recurrence relation. This is the recurrent relation. Now, and you must know that this number of pegs, n, number of disks, this is n is number of disks. This n is greater than 1. It is greater than or equal to 1. See, greater than or equal to 1. If there is only one disk, there is only just a movement from take this from here and transfer it to 2. So the problem is over. So H1 is ultimately equal to 1. That means that if there is only one disk, there is only one number of moves required to transfer it from 1 to 2 will be 1. Therefore, H1 is equal to 1. So this is our initial conditions. This is our recurrence relation. This is our relation. This is our recurrence relation, or we call it as a difference equation. Now our job is to find what is Hn in terms of n. What is Hn in terms of n, so that when we start giving when we change the values of n, you see that automatically you will get the number of moves required to transfer the pegs, the disks, number of moves required to transfer the disks from 1 to 2. See, let us start doing this. Let us suppose that. So this is the problem of Hanoi. This is a puzzle of Hanoi. Puzzle of Hanoi is nothing but you have got n disks which are arranged in the descending order. Descend means coming from the top. So descending order from the bottom or ascending order from the top, and they have to be transferred to another peg 2 using the standby one. Yes. Now the question is the minimum number of moves required to transfer the n disks from 1 to 2 with the conditions, under the conditions that only one disk, that is the move one disk at a time. You have to move only one disk at a time, and that at no point of time the bigger one should be on the smaller one. Never keep bigger on the smaller one. With these conditions, find out what is the minimum number of moves that are required to transfer the disks that are in the same or in the order in 1 to the peg 2. This is the Tower of Hanoi problem. Let us take a simple examples and then we will solve. Now our job is to solve this equation. What is this equation? This is the recurrence relation equation or the difference equation of the Tower of Hanoi problem. Now we have to solve this to get the answer. Now you see that there are 2 or 3 ways of solving it. I will teach you by a method which you can understand easily. Okay. Now let us take this. See, let us take an example of this. See. See, what is this? See, let us take this. See, if it is 1, as I told you, if it is 1, here this standby is here, this is take 1, and you transfer it to this. So this is your 2, and this comes here. So H1 is equal to 1. So this is what? Let us suppose that you have got 2 here. See? You have 2 here, and you have got a standby here. And this is your 2. This is 1 to transfer it to here. What is that you will do? The first transfer will be like this. See, bigger one will be here, and this standby is here. Transfer it to this side, and you have got here, and you have got this 1, 2. You are transferring the smaller one to the standby peg. Then this is your number 1. Then number 2 is your, see, this is 1, this is S, this is your, bring the bigger one, this is your 2. So this is number, so 2 moves are there, 2 moves were hold. That is, this bigger one has been transferred to 2. Then the next is, you have got the third one, namely this is empty now, and this also becomes empty. Transfer this, bigger is here, then smaller is here, 2. So transfer. So you have got this. So this is nothing but what? You have got here 2 into, you see, H2 will be equal to 2 into H1, see, 2 minus 1 plus 1. See, 2 into H2, this is 2 into, H2 is, it is H1 plus 1, that is equal to 3. That means, see, you have got here 3 moves. That means the minimum number of moves required is from to this is 3. So this is nothing but equal to 3. You will find that the Hn will be equal to your, it will be equal to 7. It will be equal. That means you will find that if it is 1, it is 1. If n is equal to, see, n is equal to this, then Hn. Hn is equal to 1 means 1. If it is 2 means 3. If it is 3 means 7. If it is, it will be 4 means, it will be 15. See, it will be 2 to the power of 4 minus 1. And this is 15. So like that it goes on. So this is equal to, you see, this is nothing but your, it is 2 to the power of 0 plus 1. It is 2 to the power of 1 plus 2. If it is 1, it is 2 to the power of 0 plus 1, 2 to the power of 1 plus 1, then 2 to the power of, it is 2 to the power of 1 minus 1, 2 to the power of 2 minus 1, 2 to the power of 3 minus 1, 2 to the power of 4 minus 1. So if it is, see, it will be like this. For this, this is nothing but 2 to the power of 1 minus 1. This is 2 to the power of 2 minus 1. This is 2 to the power of 3 minus 1. This is 2 to the power. Then next one will be 2 to the power. So like that it goes on. So this is nothing but, so if you find that, this will be naturally, it is, if there is 1, 2 to the power of 1. If it is 1, it is 2 to the power of 1. If it 2, 2 to the power of 2. If it is 3, it is 2 left. So this is nothing but 2 to the power of n minus 1. So Hn will be equal to 2 to the power of n minus 1. So you see that the number of moves, that is the least number of moves required to transfer n discs in the order, same order as in the peg 1 to peg 2 using a standby 1 s is 2 to the power of n minus 1 with the condition that n is greater than or equal to 1. Now, we can derive this using the solving the difference equation also. So you see that I will work out that. See, so see, it is given. See, as I told you, this is number one method. Method 1. See, we know that Hn is equal to, it is 2 to the 2 Hn minus 1 plus 1. This is a recurrence relation. I told you how this comes. This implies Hn minus 2 Hn minus 1 is equal to 1. See, let us solve. Let us solve for Hn. Once see Hn we find means, you see that we can find the number of moves required in order to shift from stem 1, peg 1 to peg 2, the n disc in the same order. That we can do. Okay. Now, see, well, let us solve for Hn. See, take Hn is equal to r to the power of n. Then, see, we have to solve this. See, what is the solution here? The solution of 1 is Hn is equal to, so this is the solution on account of homogeneous equation, solving the homogeneous equation, and this is nothing but the solution because of a particular solution because of the constant that we are having. Therefore, let us find Hn. See, take the homogeneous equation. This is nothing but what? Hn minus 0. Take call this as your 2 r to the power of n. So this is r to the power of n minus 2 r to the power of n minus 1 is equal to 0. This implies r minus 2 is equal to 0. This implies r is equal to 2. Therefore, so the complementary function, we say called as complementary function, right? So this is x and h is equal to c1 into 2 to the power of n. And HNP, because it is a constant on the right hand side, so this HNP will be simply a constant C2. C1 and C2 are constants. Therefore, Hn will be equal to C1 into 2 to the power of n plus C2. So this is the solution. Now you see that this solution must satisfy, here you must know that H1 is equal to 1. H1 is equal to 1, and this must satisfy this equation. That means this, it must satisfy the equation number 1. So this, see, call this as your 3 satisfies equation 1. equation 1 or 2. So what is that you are having now? So what is that you are having now? So substitute in this place Hn, that therefore C1 into 2 to the power of n plus C2 minus 2 into C1 into 2 to the power of n minus 1 plus C2 is equal to minus 1. So you get this to be minus 1. This implies 2C1 is equal to 2. So C1 is equal to 1. So we have got C1 is equal to 1. I have not done anything that since this is a solution, this must satisfy this equation. When you substitute, you see that on solving this, you will get C2 is equal to minus 1. But the initial condition is H1 is equal to 1. So put n is equal to 1. You will get H1 is equal to 1, C1 into 2 to the power of 1 minus 1, because C2 is equal to minus 1. So this plus 2. So C1, when you solve this, you get C1 is equal to 1. Therefore, Hn is equal to C1 is 1, 1 into 2 to the power of n, it is minus 1. So Hn is equal to 2 to the power of n minus 1. So this is what we get. So you see that what we have got here is this n is greater than 1, n is greater than 1, greater than or equal to 1. So by this what we have understood is that now you see that when you put h1, you see that when you put h1 2 to the power of 1, 2 minus 1, that is why it takes the number of moves required to transfer from peg 1 to peg 2 is 1. If you put 2, you see that you can generate the whole. That means you can generate the number of moves required to transfer the n discs. N may be 1, 2, 3, 4, 5, whatever it be. We can find out the least number of moves required to transfer the n pegs from the stem 1 to stem 2 using a standby stem. So you see that you will get. Now what is your this thing? Suppose if you put H3, see what is that you get here again? H3 is equal to, it is 2 to the power of 3 minus 1. That is equal to 7. So you can apply this. So we can get anything, say H5 or H6. So you see that it generates. That means this Hn completely generates the number of moves required to transfer the discs from stem 1 to stem 2 in the same order using another standby stem. Okay. So this is the Tower of Hanoi. See, another way of solving this will be, see it will be there, but this is the method of solving a recurrence relation. This is how we do it. I will do more number of problems and give you the method of solving by another method in the subsequent classes. Okay, thank you.